Peter, are you putting this in your calculator, or are you browsing the internet? I want an answer before I do a reveal. Don't have to give me your answer, just tell me if you got one. You got an answer, David?
Yeah.
Okay. Is there an answer in the room before I go over it? Ray, you've given up.
I've got one.
You've got one? Good.
I think, yeah.
Okay, so these are the numbers I'm going to be putting in. So I'm going to ignore my width. I don't need that as a bit of data. And certainly, well actually this is from an exam question, but it's like a part 2, 3. So certainly level 3, they should be designing questions where you've got to be thinking. So they should have some questions. Well, I don't think all the data will be superfluous, but not necessarily direct you in part A and part B where you need to apply that data. So, anyone get a me in odd rads per second?
I got it. Okay, so yeah, okay, I've got the right answer, but I've got wrong units. 1.13 times 10 to the 6, but I've put hertz, but it's not, it's
Okay.
rads per second. Okay.
Yeah. Yeah, so, yeah, don't forget, so that's omega. Omega's the rads per second one. F is going to be the hertz one. So to convert that to hertz, what would you do, David?
Times by 2 pi, divide by 2 pi.
So rad is a 2 pi. So divide by 2 pi. And just to show off, I've then changed my 1,000 into kilohertz. Yeah, makes sense. Maybe you might ask me to do a question in kilohertz. Actually, we've gone well over, so let's stop that. Right, so let's start on block 2. So block 2, let's have a stab at sort of thing. So state the difference between intrinsic and extrinsic silicon. Briefly describe conductivity of the intrinsic silicon, how it decreases with the increase of temperature. Name a region and PN junction, photodiode device that is sensitive to light, how that can be converted. The acronym for a MOS device, calculate, so do some calculations. So this is from an old exam paper. I would guess that the E would be a 3 marker, and I guess B might be because I'm doing explain, and the other ones would be 2 marks. So it should explain that in your section A, you get 6 questions. You get to choose 5 out of 6, and so when you look at the old exam papers, they're marked out 10, so they give them basically 2 marks per section. But now it's going to be probably 3 questions will have 2 marks associated with it, and 2 questions will have 3 marks associated with it.
Does it give the breakdown now?
It gives a breakdown.
Yeah.
Okay, so I'm not going to do these questions. So this is yeah, I'm not going to do the questions. This is a typical long question that you've got. So you've got more description here. So they're asking you to describe the intrinsic silicon, N-type type, P-type. So that would be very much regurgitate notes. It's supposed to be a bit more challenging, section B questions. I would have said that. And section B questions would tend to be more along the lines of design something, describe the manufacture of something, and that kind of stuff. And then we got for the MOS photocapacitor, being able to describe how that's going to work and explaining particular features. So for your block 2 equations, what have we got here? We've got the photon energy, so Planck's constant, frequency. Again, we've got the photon energy there in terms of speed of light and wavelength. So that's one form that we could write it out. Notice that you've got this one here, where the energy is in terms of electron volts. And for this one, then this is one particular example where you don't want to be doing SI units. You want to put your value in of your wavelength in terms of the micrometers. This equation, doubt would ever use that. That's how far the energy penetrates, isn't it? And same thing here. I don't think I've ever recalled these equations coming up. Then we've got conductivity, how that's dependent upon the number of number concentration of your intrinsic and N types and P types. Again, number concentration terms, conductivity and resistivity term there. And I can't say that these, I've recalled these terms have been used, but Quinn, you might be able to, can you record any questions that I've ever used them?
Actually, I think I may have seen them in a teammate question in the past. I don't think I've seen them use an angle in a second.
So, a long question here. This is taken from 2010, section B. And you're being asked to describe the production process for a PN junction. And then describe the operation of it. Notice there it's breaking it down, so you've got 6 marks there, so it's probably going to be kind of like 3 marks for a sketch and then 1 mark per piece, being able to describe something physical, electrical, or something about the process of how the photon light is detected there. On the part C, it's wanting you to state the diode equation. I don't think it's actually on our previous slide that we showed there. Sketch the current voltage graph. So just running through the answers, we did these online, so I won't label this. So certain things that you could describe to propose for the production process. So I've got as answers, production process will require starting with a substrate. And notice this is again quite high level conceptual descriptions that you want to describe, that you want to state the obvious, might not occur to you, such that you're going to have masking to end up producing P and N zones type materials. And that you could alternatively maybe do implantation to achieve that, so you might get that from masking or from splattering or whatever. And that you'd want to have some sort of metallization, i.e. to form connections. On part B, so this would require certainly a sketch or 3 marks, and then for the 3 points I had for the physical arrangements that you'd need to have your PN type quite near the surface wherever the light's going to penetrate. So that would be a physical consideration. For the electrical consideration, that the fact that, again, that wouldn't occur to me in an exam to state the obvious, that it would have to be in reverse bias for this to be in operation. That's what they're looking for there. And photons, I would probably grasp at straws and mention electron hole pairs, and I would have got a mark there. So it's not necessarily jumping at the page of what the question is requiring. and it is in most cases stating the obvious. So we didn't actually have this equation that's further down on the equation sheet, but that would be the equation that you'd want to do for the current. Then break down the particular terms. Boltzmann constant. Now something like, say, Boltzmann's constant, you could relate that back to your data sheet. So if you wanted to show off that you know how to spell Boltzmann, look at your data sheet and you find Boltzmann there, for example. So be aware of your data sheet if you're looking for terms and you want to know which terms that are available on that data sheet. So they want a sketch like this for the part D of the question. That say that we're operating in reverse bias, and how you're going to have this dark current here, and the voltage is basically going to be basically independent of voltage.
Sorry, Ian, on that last question we had to quote formula. If you put something like saturation current instead of reverse saturation current, would you like lose a mark?
No. And then, we're looking forward to explain the graph. So the fact that the instant light is going to basically shift that graph up and down. Okay, so the topics that you need to revise for block 2 is obviously the intrinsic, extrinsic types, doping, how that leads to resistivity. Let's say resistivity, and how that's then dependent upon temperature, and what else? Yeah, well, obviously doping as well. The concepts of electron hole pairs, p-types, n-types, being able to differentiate the two. Then you've got 3 applications that you want to be able to describe. So start off with the simplest one, the photoconductor, photodiodes, photocapacitors. What I would recommend that you do is you learn how to manufacture a complementary MOS device, because then you'll cover the manufacture of all the other techniques. The concept that light is a photon, basic principles of displays. We had some stuff on display, so maybe that might not come up, and techniques of manufacture. In terms of what's you need to cover in terms of on the blocks, in the principal stuff, being able to describe a band gap. What else? Being able to describe maybe how the operation of a p-n junction works. Again, I said photons. Techniques, go for CMOS fabrication. And then that. So, summary of the intrinsic conductivity. So I'm working in sevens here. We could have that all the electrons on the outer shell are involved in the electrical current, but they need to be have a certain warmth to them. So everything's going to be, the electrons are all going to be frozen in their crystal structure. Electrons will hop around, and then the holes will be moving in the opposite direction. Holes don't technically exist really, do they? But because an electron then having to move into that space where the hole is, that means that that hole has a lower mobility. You want to model it as a hole. Because you're going to have the same number of once an electron is released from the crystal structure, you're then going to generate a hole. So you're going to have equal numbers of electron conducting the current as the holes, and they will both contribute to the electrical current resistance. For extrinsic, so what can we say there? So first, let's state the obvious. You need some doping. The doping now means that we can control the resistivity, or rather the conductivity in this case. We're more interested in that. The doping also means that any thermal effects are now going to be swamped by the fact that we've got doping. It's there. Donor, I remember donor, and I remember it. My numeric in my brain is to spot the N, and that's my N type. My acceptor, and that's got a P in it, That's going to be my P time. Okay, so donor, I'm giving you have an extra electron, and accept, I'm going to accept an electron, and therefore I'm giving you a hole. In this particular case, because the acceptors is based upon extra holes, we therefore expect lower mobility. Right. I think we'll squeeze Gwyn in.
Make a break for lunch afterwards.
We have a later lunch. But go off a little bit of schedule.
Okay, again,